Welcome back to the deep dive. Today, we are tackling what is, I think, maybe one of the greatest paradoxes in space travel.
And definitely one of the biggest misconceptions in all of physics.
For sure. So, when you watch that footage of astronauts, inside the International Space Station, the ISS, just drifting so gently, what's the first thing that springs to mind?
For almost everyone, the immediate logical answer is, well, there's no gravity in space.
Right.
It makes sense, doesn't it? You think, okay, if you just travel far enough away from Earth, the force that keeps us all grounded, it just sort of disappears.
But that idea, as intuitive as it feels, is just, it's fundamentally wrong.
Completely wrong.
And that's really the starting point for our deep dive today, because we have to just firmly debunk that right at the top. Gravity does not disappear.
In fact, and this is the really wild part, if you follow the physics all the way through, you realize gravity is the exact reason they're floating.
It's a classic physics riddle, isn't it?
It is. So today, our mission is to unpack this, this really complex idea, but do it slowly. We'll guide you through the real science of it all, of orbital mechanics and weightlessness.
The goal here is for you to be able to look at that footage of an astronaut floating and know, really know, what's happening.
Exactly. To see the physics behind what looks like magic.
Okay, so let's start with the basics, with the conceptual clarity we need. The confusion really starts because we use two words, gravity and weight, almost interchangeably.
We do. In daily life, they mean the same thing, but in physics, they are dramatically different.
So what is that key distinction? What do we need to grasp?
Well, gravity is a force. It's a universal attraction between any two objects that have mass. It is always there, always pulling.
Okay, so a constant pull.
Right. But weight is not a force. It's more of a measurement of resistance. Yeah. Weight is what you feel when gravity's pulling on you. And crucially, something is pushing back.
Like the ground pushing up on my feet right now.
Exactly like that. Or the chair you're sitting on. That pushback force is what your brain interprets as weight.
So that's it. The pull of gravity is always there, but the sensation of weight, that feeling of heaviness, depends completely on something blocking that pull.
You've got it. And that simple distinction, that is the key that unlocks this whole mystery.
No opposing pushback.
Means no weight. You can be in an incredibly strong gravitational field, but if nothing is resisting that pull on you, you will feel completely and utterly weightless.
All right, now we're getting to the really counterintuitive part. I think most of us, when we see the ISS, we picture it way out there, halfway to the moon.
Far beyond gravity's reach, yeah, that's the common image.
We need to just completely reset that expectation. Just how far away are those astronauts?
They are surprisingly close. The International Space Station orbits Earth at an altitude of only about 400 kilometers.
400 kilometers?
Yeah.
That's like a day trip in a car.
It is. It's not the deep, empty void of space that most people are imagining.
So what does that proximity mean for the strength of gravity?
It means gravity is still incredibly powerful up there. At 400 kilometers, Earth's gravitational field is still about 90% as strong as it is right here on the surface.
90%?
90.
Wow, so the pull they feel is, it's almost identical to what we feel standing on the ground.
It is.
Okay, so if Earth's gravity is pulling the ISS and everyone inside it with 90% of its full power, they should just be yanked straight back down. Why haven't they fallen?
And that is the perfect question. The shocking but 100% accurate answer is they are falling.
They are.
They are falling constantly, every second of every day.
Hey, okay, hold on. If the station is continuously falling and gravity is pulling it with that much force, why doesn't it just hit the atmosphere and burn up? This must be the secret to how orbit works.
It is. This is the whole mechanism. It's all about the immense sideways speed, the horizontal velocity that the station has.
Yep.
So the station is in a perpetual state of free fall toward Earth, but it's also traveling sideways so incredibly fast
Then it just misses.
that it continually misses the planet. Exactly.
How fast are we talking about here? Give us a sense of that speed.
They're moving at approximately 7.7 kilometers per second.
Per second.
To put that in perspective, that's about 17,000 miles per hour.
17,000 miles per hour. That's fast enough to get from New York to LA in, less than 12 minutes?
That's right. It's a truly blistering speed.
So the whole point of those huge rockets isn't just to lift them up.
No, getting up is the easy part.
The main job is to accelerate them sideways to this unbelievable velocity.
Precisely. If you just lifted the station 400 kilometers up and, just stopped it there, it would immediately fall straight back to Earth.
Like a stone.
Right. The whole orbital trick comes from Newton's idea of continuously falling around a curve. As the station falls, say, a few meters toward Earth,
The planet itself curves away underneath it by that same amount.
by that exact same amount. The station falls, the Earth curves, and it just keeps on missing the ground. That dynamic balance, that continuous falling and missing, that is what we call an orbit.
So the ISS is just perpetually on the brink of crashing, but its crazy sideways momentum keeps it locked in this perfect arc.
It's a dynamic equilibrium. And this brings up a really important point you touched on. What keeps that speed from, decaying?
Right, because even at 400 kilometers up, there's still a little bit of atmosphere, isn't there? A few molecules here and there.
There is. It's very, very thin, but it's not a perfect vacuum. So that friction, it acts like a very subtle brake.
So that 17,000 mile per hour speed must be bleeding off over time.
It is. If you just left it alone, the ISS would gradually spiral inward and eventually burn up.
So how do they stop that?
To counteract it, the station periodically has to fire its thrusters, just little bursts, in a maneuver they call a reboost.
To push itself back up.
Exactly. To regain that critical speed and altitude. Maintaining an orbit is an active process, not a static one.
It fundamentally changes how I picture it. It's not a calm, parked object. It's a terrifyingly precise, high-speed balancing act.
It really is.
And this state of constant free fall, that leads us directly to the environment inside the station, which we call microgravity.
Right. And microgravity just means that the effects of gravity are, well, they're not gone. They're just being constantly canceled out by the act of falling.
Because everything is falling at the same rate.
Everything. The structure of the station, the air inside, the equipment, the astronauts, it's all falling together in unison.
So nothing pushes back on anything else.
And if nothing pushes back,
You feel no weight.
you feel no weight.
This is where that fantastic thought experiment comes in handy, the one about the elevator.
Yes, the snapping elevator cable. It's a bit grim, but it works perfectly.
So walk us through it.
Okay, imagine you're in a very, very tall elevator. And hypothetically, the cable snaps.
A terrifying thought.
It is. But for that brief, uncontrolled descent, the floor of the elevator car is falling away from your feet at the exact same rate that you're falling.
So the floor isn't pushing up on you anymore.
Exactly. And for those few seconds, you'd feel completely weightless. You would float relative to the inside of the car.
Space is just that same idea, but controlled and stretched out forever.
Oh, definitely. That's all it is.
So when we see an astronaut just floating down a corridor, they are exactly like that person in the falling elevator.
That's right.
But what happens when you don't have that point of reference? I mean, how do they manage simple things when up and down just stop existing?
It changes everything. They have to rely on tethers and handholds for almost every task, even sleeping.
Sleeping?
Yeah, you have to strap yourself into a sleeping bag that's attached to a wall. Otherwise, the small air currents from the ventilation system would just have you bumping into things all night.
And getting around is just pushing off a wall and floating until you hit another one?
Pure inertia. You push to start and you grab something to stop. The concepts of floor and ceiling become totally arbitrary.
And this environment, it also changes the basic rules of how materials behave, which is really why the ISS is up there as a lab in the first place.
Absolutely. We were saying that if gravity isn't the dominant force, then other, much weaker forces get to take charge.
You're talking about things like surface tension.
Surface tension is the perfect example. Here on Earth, gravity is king. It pulls water down, it forces it into the shape of its container.
It makes a puddle.
Right. But in microgravity, gravity's pull is being canceled out. So what takes over is the natural tendency of liquid molecules to stick together. That's surface tension.
And the most efficient shape for minimizing surface area is a sphere.
A perfect sphere. And that's why you see those iconic floating balls of water. Physics hasn't disappeared. A different force is just running the show.
And that has some amazing implications for research, right? Like growing crystals.
A huge one. On Earth, when scientists try to grow very pure crystals, gravity gets in the way. It causes convection. It causes the heavier elements to settle. It creates flaws.
But in orbit, without that constant pull, you can grow almost perfect crystals.
Near perfect, which are incredibly valuable for things like advanced electronics, new medicines. It's a huge reason for the research on the ISS.
So space isn't a place where physics disappears. It's more like a perfect lab where the minor league forces get their chance to play in the major leagues.
That's a great way to put it. Different forces take control.
Okay, so we've sorted out the paradox of close orbit. Now let's zoom out, way out.
Deep space.
Yeah. A listener might still be thinking, okay, I get it for the ISS, but what if we travel truly far away? Billions of miles from any planet or star. Is there gravity there? Does it finally hit zero?
And the answer, amazingly, is still no.
Still no.
Gravity exists everywhere because matter exists everywhere. It is a fundamental property of the universe. It just gets exponentially weaker with distance.
So even in those huge dark voids between galaxies.
Gravity is still there. It's acting, incredibly feebly, but it's still tugging on galaxies trillions of miles away.
Yeah.
True zero gravity is just a theoretical idea.
You'd have to be an infinite distance away from everything.
From all matter in the entire universe, which, is practically impossible.
Which makes understanding what's happening on the ISS even more important. The feeling of weightlessness isn't a sign that gravity is gone.
It's a sign of gravity's perfect, unimpeded action.
That is the ultimate takeaway here. Astronauts float not because they've escaped gravity's pull,
But because they are in a constant, perfect free fall, with nothing pushing back against them. They are obeying gravity absolutely perfectly.
so the next time you see those images of an astronaut floating, you can remember they aren't defying gravity at all.
They're submitting to it with incredible speed and precision.
And if we connect that knowledge to the biggest possible picture, we realize this isn't some special trick we invented for space stations.
No, it's universal. The same physics governs the entire cosmos. The moon is perpetually falling toward the Earth.
But because of its orbital speed, it perpetually misses.
And the Earth is perpetually falling toward the sun.
Motion and gravity are always locked in this cosmic dance. Nothing is ever really standing still.
Everything is locked into a curved path by gravity. It is an incredibly precise and really a beautifully choreographed system, all governed by the pull of mass and the momentum needed to continuously miss the target.
So if we zoom out one last time, knowing that the same precision that holds a 400-ton space station in a perfect high-speed balance is the exact same precision that governs the orbits of planets, the movement of galaxies, what does that tell us about the ultimate mechanical laws of the universe? Is this perfect predictability the greatest mystery, or is it the simplest, most profound necessity?
A good question to ponder.
Thank you for diving deep with us today.